Assalamu alaikum from the Ohio State University. I'm honored to be part of this international hybrid conference on molecular modeling and spectroscopy. So I'll be talking about the spectroscopy of chlorine and for astrophysical modeling. Then spectroscopy is the best way to obtain the maximum information of elements or molecules and to understand them and for proper application of these elements. The most powerful telescope at this time in space is the James Webb Space Telescope, JWST, as shown here. It has an extremely sensitive surface and a gold-plated surface which can catch photons in the infrared region of 0.6 to 28.5 microns, which are very weak, traveling in space. One purpose of this telescope is to get the spectroscopy of elements so that we can find out the information about the cosmic time and also to get any information in the life form that can exist in the universe outside the Earth. It has already been giving us a lot of information. And this slide shows that as one of the earliest spectrum that we obtained from its from JWST. There is the top panel shows the galaxies which are very, very old, close to the creation of the universe. And there's the constellation, it's called SMACS constellation, and behind it, there is a galaxy which is 13.1 billion years old, and our universe is 13.8 billion years old. When that the light was analyzed for spectroscopy, we found that it has, that galaxy had not only hydrogen and also oxygen and neon. So this is a wonder because that early stage of the cosmic time, that elements like oxygen or neon would be formed in beyond hydrogen, helium, and lithium, and is kind of surprising. These two are like elements of even atomic number. We have been studying elements, particularly the even atomic number. And for example, in this slide, it shows the abundances of elements with the atomic number 1 to 50, and then the rest one is the heavier elements. And we can see that, you know, the zigzag means that the abundances are high for the even atomic number elements and lower for the odd atomic numbers. So the reason is probably that protons, when the two protons fuse together in the core of the star to form an alpha particle or helium nucleus, then probability of this alpha particle to fuse with another alpha particle to make another element of even atomic number is higher than the alpha particle joining or fusing another proton to make an odd number atomic number element. Chlorine is odd atomic number element. It is 17, as you see here, is 17. It is less abundant, like in the lower curves, less abundant and less observed, and that's why it has been studied the least. However, chlorine has been familiar to us very much. Chlorine is, for example, is used to disinfect the water we drink. It is also used for various bleaching purposes. And also chlorine compound like sodium chloride, salt, it is also used to melt the snow during the winter time, like currently. And also we need chlorine for our body, and we get that supplement through the salt, sodium chloride. And chlorine is also used for various industrial purposes. But recently, this chlorine has been found in the cool plasma of planetary nebulae. This is a picture of a planetary nebulae, which is actually an status of a dying star. And it has cooler plasma outward, and chlorine 3 particularly has been observed. And then so chlorine 2 exists, and it gets photoionized by the surrounding photons, and chlorine 3 is formed. It also has been seen in the moon Io of the planet Jupiter. Not and then recently, its signals have been detected by SDSS, means like Slow and Digital Sky Survey, from the galaxy of NGC 5515. And here we can see the spectrum. It is a very weak spectrum. You can see the flux ratio here, but we can see, a few peaks, one peak here, and there is a peak, but the orange, the predicted curve, it shows that should be another peak, but it is not visible here, but another peak is visible here, and maybe there is another one here. So I have written down these 4 peaks at least, and at these wavelengths. So this wavelength range is also very small, about 5500 to 5600 in the visible range. The modeling of this spectrum, and now using this line, we first identify the lines. After that, we do modeling with the plasma presence, and we can get a lot of information and of temperature, density, and how chlorine has been formed, what kind of environment it has, and that is called modeling spectral after spectral analysis. So so we need to study the processes which is creating this spectra. There are 4 ways that photons can come out or absorbed and form spectral lines. So these the 4 ways. The first one is, everyone knows, it's photo-excitation or de-excitation. That means an atom can absorb a photon and be excited from level E1 to level 2, and then it can come down. So it can have absorption line to go up, or it can come down and give us the emission lines. And so we can see these kind of lines in the grating and spectra, and these lines can be seen both in absorption and emission. That's one way. The second one is photoionization. So photons are coming, and this electron, for example, absorb the photon and leave this ion. So it is absorbing the photon, so that line can be seen in the absorption and spectrum. The third one is electron impact excitation. Like electrons, where traveling electrons can collide with an atom or ion and excite one electron to a higher orbit, and by giving out part of its energy, then this atom is excited, where the electron has lost some energy, but this excited ion can give out a photon, and which we can catch through the telescope and study the spectrum and get a lot of information. The fourth process is electron-ion recombination, and the lines are seen in the emission spectrum. So for example, this is an ion with a vacancy, and an electron traveling can see the vacancy here. So it can just go there and give out its extra energy in terms of a photon, which comes out as a recombination line as the electron is dropping down to some bound orbit. But I'll be talking about the first 2 processes, photo-excitation and photoionization, that we have studied for chlorine. So this This is a process that we have been talking about. Third, so the atomic parameters that we calculated for this process is the oscillatory strength, or F, for excitation, and for de-excitation, no, we calculate the radiative decay rate, or the A values. Okay, so and then we can calculate the probability of excitation from state I to state J, and be due to the interaction of, this is the electron momentum, an atomic electron, and the field, the photon field, which is IKR, which is an expansion of many terms. And when we do the integration of this probability, the first term gives us a dipole allowed transition, and other terms gives other kinds of transition, but this is the most dominating transition. So this is the matrix element for dipole allowed transition, where D is the dipole operator and the wave function of two different bound state wave function. And we can just calculate this matrix element to get the line strength, and they take the mod square. And once we get the line strength, we can calculate, like oscillatory strength from the line strength, and or radiative decay rate, or the cross section. So this, so I will show the results from chlorine spectrum. This is for the chlorine 2 spectrum that I have plotted with over 16,000 transitions. This is the full spectrum from X-ray to the going in far infrared region, and we can see that most of the lines are in this region, in the infrared region. So to see the its presence in the X-ray, or the low energy, shorter wavelengths, lower X-ray to optical, like here up to 8,000 angstrom. When you plotted the lines, we see that it has a weak presence in the optical region, but a strong presence in the infrared region. Then I have studied also the spectrum of chlorine 3, and this is the whole spectrum of chlorine 3. It has over 83,000 transitions. Again, we can see that it is more dense here, that there are a lot more lines in the infrared region than in the far in the far infrared region. And so what I did, as we seen in that particular spectrum of SDSs, so I just plotted that very short wavelength range of 5,500 to 5,600 spectrum from here, and I can see this is the spectrum I get, and we can see that it is a pretty weak spectrum as expected. And this red, those now the red lines are the positions that I have collected from that spectrum, and we can see that there are some signals, but there's a shift. This plot is without the plasma effect, and we can see that the observed spectra is in the shorter wavelength range. That means the wavelength is shorter. All are shifted, looks like, and so it could be that the red shifted and the object is going away. So this is the way we can identify and observe the spectrum and analyze. We really have to do the modeling and to find out the speed of the object, and then we can do the modeling to get the temperature and density of the plasma where the lines have formed. And this, okay, the second process that we have studied is photoionization. As I mentioned, the photon is absorbed by the electron and get ejected out, which is photoionization. So this is the simple, direct photoionization. But in nature, it is not so simple, because in between like photon absorption and going out, an intermediate state can form, which has two electrons excited. Usually one is bound, the other one is in the continuum. These two form, and then it breaks down. But this happens all the time. So there's an intermediate state, and this state is called the autoionizing state. Is it also actually it is a Rydberg state, but because it breaks down, it's called autoionizing state. And presence of this autoionizing state, it creates a resonant line or a line in this in the cross section or spectrum. But this is very important to consider this intermediate states mathematically, so that resonances can be produced theoretically. And this process is very important. It is happening all the time on all plasmas, particularly the plasma which is illuminated by some radiative force, like this. Nebula. This nebula is a Lambda Centauri nebula, which has a lot of photons around, and plasma is being ionized by photons. Or also we can have the plasma ionized, photoionized by photons around a star, like our own sun. So this corona also has plasma being ionized by the photons. So whenever we want to do modeling of this kind of plasma, we need photoionization cross-section. Not only for that, we also need photoionization cross-section to calculate the ionization fraction of an element. And then, like, this is the balance equation here. At the left side, sigma pi is the photoionization cross-section, and this is the flux which is causing the ionization. This is the ionization part, and this is the it is balanced by the recombination part, where sigma RC is the recombination rate coefficient, and these are like density factors, the electron and the ion. So how do we incorporate this intermediate state in the calculation is through the wave function, which I will explain. And to do that, we have to look at the diagram, energy diagram of those autoionizing states. So this is the energy diagram. You can see this particular on the left side, this purple diagram, it shows the various bound state, and this is continuum or free energy region. So this atom is being ionized and become an ion at electron energy is 0. So this is just simply, electron is going into continuum. So this is direct photoionization. However, this we can have this ion itself to be excited at various excited states. Below each excited states, the quantum states exist, the quantum energy, which are Rydberg states. And these states form when there's an electron combining with this ion, form a quasi-bound state at these energies, and these energies are given by this formula. Okay. So whenever an electron combining with this ion form this kind of state, a short-lived state in the continuum, and we call that autoionizing state, it breaks down and introduces a resonance or line in the spectrum. So these kind of lines appear when we have this kind of states forming. Otherwise, if we don't form that state, there is no line, it will be just a smooth curve like that. So there is another, so these are the resonances. We also talk about another kind of resonance. So we call it Pack or Seaton resonance, who actually explain that kind of resonance, which are not line resonances, which are like a kind of broad features, but still it is a resonance. Okay, to take into account of this intermediate state, the only way we can do it is through close coupling approximation of the wave function expansion. So this is the wave function representing this whole atom. So what we think in this approximation, the outer electron is the interacting electron, and it is interacting with all the electrons, or as a whole, the core ion. So we write the wave function as the product of core ion wave function multiplied by this interacting electron wave function. This is just part of this express to show the orthogonality condition. So the advantage of writing wave function in this manner is that we can include this sum not only ground level of the core, various excited levels of the core ion. So in that way, we have excited core when we take the transition matrix element and we have the interact with the bound state and continuum states, we can create the resonances naturally. But if we substitute this kind of expansion in the Schrodinger equation, we end up with a set of coupled equations, which we usually solve by a method called R matrix method. And because this Hamiltonian becomes a large matrix, we have to solve it using the R matrix method. And when you solve it, if the eigenvalues, which are the energies, if an eigenvalue is coming out negative, it is a bound state. And if it is coming out positive, then the corresponding solution is the continuum or free state. Once we have these wave functions, we can calculate the transition matrix elements for various quantities. This one slide shows an example of the wave function that we have in close coupling approximation. So this is the wave function expansion for chlorine 2. And it has core ion excitation up to 45 levels, from 1 to 45 levels. So all these levels are included in the wave function expansion. So it is a very large wave function, and it also creates a very large Hamilton matrix. So the computations are large, and so we use package of codes, which are called R matrix codes. Okay, so we calculate the transition matrix element, just like we calculate transition matrix element for bound transition. Here it is, one is state is bound, the other state is free. So that is the only difference. In a similar manner, we can calculate the line strength. And when we calculate the line strength, the angular part will give this kind of selection rules, which state that electron can go to. And then we can calculate the photoionization cross section. Okay, because the computations are large, so there are various stages that we go through, as I mentioned. So the package is called R matrix, a package of codes. So for example, and here we can see all these boxes. We can go through this way path or this path or that path. So usually we choose this way. So we go through various stages until ultimately we calculate the dipole matrix element, the Hamilton matrix, and bound wave function, free wave function, and the final products are given here. Energy levels, oscillatory strength, photoionization cross sections, deconduction cross sections, and collision strengths. Okay. And now I'm showing the results. So here I can see the photoionization cross sections of a number of levels, 1 to 5 levels of chlorine 2. These levels all belong to the ground configuration. Only the top one is the ground level. Okay, triplet P0 level. And you can see various lines here. Now these are the lines or the resonances in the photoionization cross section, and we can see there are a lot of them. And these lines will not necessarily show up in the spectrum. If the lines are very strong and kind of isolated, usually those lines can show up in the spectrum as absorption lines. Otherwise, most of the time, these lines, because they are very close and they are not very strong like bound transition, they get dissolved by the plasma density and temperature, and that dissolved part now impacts the background or the shape of the spectrum. Okay, to prove that now accuracy of our calculations or the feature that we see in the photon cross section theoretically can be proved or benchmarked by experiment. This plot showing the experimental measurement of photoionization spectrum of chlorine 2 at the Lawrence Berkeley National Laboratory, this dome-shaped building underneath which there's a setup, synchrotron setup, and we can use the setup to get one setup to carry out the photoionization measurement. So this measurement was carried out. My colleague who is also giving the talk, Guillermo Hinojosa, this is the spectrum they measured and published. But this spectrum is not a spectrum of the ground level. Whenever they try to measure, usually the focus is on the ground level, but the energy bandwidth is not perfect and not just a ground level. Other levels also exist and they contribute to form the spectrum. So this spectrum has features of a number of levels. To understand that, we have to identify and do the calculation. So this is the spectrum that both the theoretical and experimental. The top panel shows the same spectrum I showed on the last or the previous slide, and these are the cross sections for 9 levels of chlorine 2. And these cross sections have a lot of lines or resonances. And when you match the top resonances with the calculated ones, so we can identify where this resonance is being formed. For example, this resonance is formed from the ground level of chlorine 2. Or this one, this resonance probably formed right at ground level, but it also can be seen in this excited level. So we can just identify the positions of all these resonances in these calculated cross sections and tell which levels existed in the experimental beam and also which produce these lines. But the intensity of the observed spectrum not necessarily will match the calculated ones because there are many other factors are involved. The calculated ones are we just calculate at a fine energy mesh and we plot whatever we see. But in the experiment, what they have various kind of abundances. Some levels have more abundance than the others, and so depending on that factor, now we can have the intensity of the lines. And not only that, there is also bandwidth. Like in the detector, they have a bandwidth to detect. So it cannot detect all the resonances, not fine resonance. And it has because of the bandwidth, it can average out all the resonances to a particular form. So to match this observed spectrum, what we can do, we can convolve these resonances and see how much we can simulate the observed spectrum. So this is where we have this convolved, those theoretical cross section, so that we can see the similarities, more similarities with this observed spectrum of photoionization of chlorine 2. And if you can see that, we can tell the positions of various resonances and from the cross sections of various levels, and that's how we identify. We can even identify the spectroscopic identification once we know where this excitation threshold of the ion core exists, and then we can go through the analysis and find out the exact identification of the resonances. Okay. Now, this one is again experimental photoionization cross sections of chlorine 3, not chlorine 2. It was this measurement has also been carried out by Professor Guillermo Hinojosa and his team, and these are the theoretical calculations from the R matrix method, and that I carried out to do the spectral analysis of this spectrum. And here we have about 8 levels. And this is the ground level cross section, and we can see that this dominant part certainly comes from this ground level, and we can see other resonances. And so what we did, we tried to identify the presence of all these resonances, and we tried to search, where do these exist and which level they exist. And actually we have been identified, and all these resonances exist in this calculated cross sections. So what I did this time, I convolved them with the experimental weight so that it can simulate this experimental spectrum. Not only convolve, I sum them, combine them together and to form this spectrum. Okay, so this is the observed spectrum, and that is the calculated or predicted spectrum. And these arrows point, the arrows point all these resonances of the lines, and the same arrows are also showing here the presence of these resonances in this spectrum. So again, the positions are identified. Only the peaks values are not the same, because as I mentioned, there are a number of factors involved to analyze this observed spectrum. So that's how we benchmark the experimental photoionization cross-section by the theoretical cross-section, also a theoretical cross-section by the experimental ones. So I think my last slide is this a photoionization cross-section of this is chlorine 2, but it's a theoretical cross-section. There are 3 cross-sections of 3 excited levels, and showing now they are not a low lying, they're relatively high lying excited levels, these levels, and they are written here, these levels. And not only that, we see the line resonances, we can see broad feature, and these broad features are produced by these arrow positions, which are the excitations of the core ion. And these the resonances are called Seaton resonances, or sometimes it also called pack resonances. When they are combined, they form a broad feature, very broad feature. And these features obviously are very important because it also enhances the background, considerably by orders of magnitude. So they have impact in high temperature plasmas for spectral analysis, for opacity, for abundance, and etc. So, but this has not been observed in the experiment yet, because the experimenter does not go to these highly excited levels yet, and then high energy to observe these features. But with the advances in the instrument, I think it should be observed soon, because like the Spectra setup in Germany, which has high energy range, and possibly it will be able to study the highly excited states of ion. So this is the way we do spectral analysis and study the atomic processes which produce this spectrum. Thank you very much. I'll take the question when I get the time. So I'll stop it. Sharing.